In this video, we're going to ask a fairly reasonable question, I think, for most students, which is where might you encounter an eigenvector or eigenvalue after this course? And we're just going to dip our toe in this just to let you know what some of the flavors of those exemplars are. And we're going to just cover these very briefly. For students going into the geology, civil, mech type of thing, mining as well, this stress tensor is something that you'll see. You'll see these little cubes. Imagine a rock or a sample that's being pressurized in some way. And this turns out to be fairly complicated. You've got stresses and you've actually got shears for these off-diagonal things. And you end up trying to look at the microcosm of the three faces on this cube. And it turns out that if you pick the right axis, which ends up being nice perpendicular axes, you can reconstruct this into three simple stresses. And these are called the principal stresses. And it should come as zero shock at all that sigma 1, sigma 2, and sigma 3 are the eigenvalues, and that these new directions, new axes here, the ones that make everything simple, happen to be the eigenvectors of the stress matrix here. And again, it's just this idea of the first basis you pick may not be well aligned to how things are actually working in the force world, in this case, stress-strain world. And so if you just pick better axes, which happen to be the eigenvectors, you get a much simpler problem to worry about and to consider. Now, something you've all seen with APSC 172 is the second derivative matrix here. And remember, the second derivative test was about curvatures in 2 dimensions. We get to tell saddles apart from local maxes and local mins with the second derivative test. Well, not too surprisingly, that matrix is problematic or hard to work with, involves these weird second partials that are hard to explain, only because the x and y axes aren't necessarily the most natural axes to use for your function. If we take a look along the eigenvectors, in the plane here, we'd end up with 2 eigenvectors for this matrix here, and they're the natural directions where you see the most extreme curvatures. And what you get here are what you'd call the natural second derivatives, and these would be the eigenvalues of the second derivative matrix. So again, we have this idea of properties that can be explained in the xy axes, but it's really nicer if you can explain them in maybe slightly different axes. It'll simplify the picture, and you can simply describe curvature in a much more straightforward way than you can when you use the default but not necessarily best matched x and y axes. In the same vein, if you get data, what you often find, here is sort of a cloud of 3D data points, is that most of the data is kind of spread around some axis, some plane, and you can see that through the covariance matrix. Well, it turns out that if you take that covariance matrix in the default axes and decide, no, I don't really want those axes. Let me take this axis, and maybe an axis off this plane, which you can't really see as easily in 3D, but you can imagine getting those 3 axes. Oh wait, those axes are the eigenvectors of the covariance matrix. And what you can also find, and this is what this particular approach, principal component analysis, is used for, among other things, is to reduce the data. If this data is sprawling in the natural 3 dimensions we use, the x, y, and z's, but if you look at it along these special directions, these eigenvector directions, it turns out this last direction, there's not as much variation that way, so you can kind of throw that away. You project everything back down to a plane. Now you have roughly the same distribution of points. You've just thrown away a little information, but you can work with this data much more easily. And not too surprisingly, the eigenvalues end up being the magnitudes that help you determine how much spread is in the data. Again, that's going to be for a data analysis course later on. As one of the most famous linear algebra examples, one of Google's claims to fame when it first started was the idea of using the graph connection of websites. So all of these things here are websites. And building an idea that this site is important not because it has a lot of content, but because it's pointed to by other people. And basically, all these other sites are vouching for the helpfulness of this. And you can imagine all the people that cite Wikipedia, so a bunch of things point to Wikipedia, think, well, that's important to capture. Well, what you can do is, in a smaller scale here, you can build a relationship between the websites and say, well, this site seems to point, half of its links go to here, half its links go to here. You get this fairly complicated network, but you can express it in terms of a matrix. And through a little bit of extra fiddling, you start realizing that, well, what do I mean by this site here being maybe more important than this one? Well, the importance is going to satisfy a relationship that this matrix A times the site importances ends up being the site. Oh, hey, this is our eigenequation. The site importances are going to be what they are if they match A times that vector equals the same vector again with a lambda of 1, as it turns out. And this can be a useful input for trying to rank the output for a search. Out of all the sites that match a particular text string, which one should you prioritize? Well, this gives you one metric to allow that. Image processing is also a big consumer of eigenvalues and eigenvectors. You can get some fun videos on YouTube looking at eigenfaces. The idea here is that if you have, sort of like principal component analysis, you might have a bank of faces and you try to find the principal directions, but now the directions are actually images. It gets a little meta. You have to think about data forms and stuff like that. And we're just going to hit the highlights here. But you have building blocks that can be used to describe all possible faces. And the idea is you might have thousands of these, but they're prioritized in some sense by how much of a contribution they make on average to all the faces in a data bank. And so here we have Sheryl Crow would be some linear combination of these basis vectors. Here, basis faces or eigenfaces. And the idea is that your image as well, if you took a picture of yourself, you could reconstruct it with some number of these eigenfaces. And there's an idea of data approximation. Maybe you get more accuracy if you go on further, very similar to 172 series calculations. But there's also the sort of ethereal freakiness to these faces that are not faces built into this approach. So that's just kind of fun. And last but certainly not least, just thinking about the eng-phys people, if you take a look at the physics involved with waves and quantum, which is built on waves, you see equations like these, and just looking at this equation, the second derivative of this function x equals, oh, this is a complex process, and this is a scalar. This can actually be modeled. The second derivative can be represented in some way as a linear transformation, because derivatives are linear. And we want to find the functions that when we take the second derivative, we get the same thing back, but scaled. And that's exactly the eigencondition again, or the eigenequation. Yes, we have to dig a little deeper to figure out what that means for us, but the same kind of thing, I'm glossing heavily here, shows up even in the Schrodinger wave equation for quantum. You can see it's this repeat of the same unknown function, transformed-ish with scalings, but you can feel this eigen idea that transforming this function somehow gives you the same function back, but maybe scaled. That turns out to be crucial for understanding, again, what's the underlying building blocks or important ingredients for these functions. It's the same kind of eigen process we went through for matrices and vectors. And with that, we will end our lectures for the course, and we wish you all the best of luck on your final exams, and also good luck for the summer if that's where you are, or in the fall if you're taking this in the summer.